Okay, looking at problem 6 for November 9th, 2012, HL Chem, paper 2. First question asks us to define the rate of reaction. Could be said as the change in concentration of reactant or product over time. They would also accept rate of change of concentration. Okay, so to temperature and the addition of catalyst, two factors that can affect the rate of a reaction state to others. These would be concentration of reactant and particle size / surface area. They also mention pressure, which I guess they're assuming it's a gas. And they also mention light. These two kind of confuse me, but okay. Okay, so in the reaction below, state one method that can be used to measure the rate of the reaction. If you notice, you have charged particles on the reactant side, no charged particles on the other. So you could look at the conductivity, which should decrease over time as you make those more neutral products. You could also look at pH. It should be getting less acidic as the reaction progresses. This one you have to be careful of. Defining the activation energy, you need to say the minimum amount of energy, or minimum energy needed. Gosh, that's needed. Needed to start a reaction. This they ask you for a Maxwell-Boltzmann energy distribution curve. There are a couple of things that they're looking for specifically. They want the x-axis to indicate energy. You can't say kinetic energy, right? But it's got to say energy. For the y-axis, you can either say particles or fraction of particles or probability. Okay, and when it's looking for a curve, they're looking for a asymmetric curve, distribution curve. You need to start at the 0 point, going up and then over. Okay, for the higher temperature one, the area under the curve should actually be the same because it is the same number of particles. Be sure not to touch the axes, but you do have to start at the 0 point. This would be T1, this would be T2. Okay. These seem to be a tough question. The concentration of reaction X against time for a zero order. Even though it's zero order, the concentration of that reactant, because your X going to products, is going to decrease over time. The rate of reaction for X for a zero is the one that's going to have the zero slope. That should be a straight line. The rate of reaction against the concentration of X for a first order. Remember the rate equation or the rate expression is rate is equal to K times the concentration of X. You should see that this is a linear relationship. It would look like that. Okay. Okay, so let's look at the next problem here. I'll make it just a little bigger. All right, so we're asked to deduce distribution given that data. All right, remember that the rate expression is equal to the rate constant times the concentration of the one reactant to the x power and then the other reactant to some power y. And we have to look at the experimental data to determine that. So if we look at trial 1 and the change going to 2, we see that this concentration is multiplied by 0.5. So you multiply this times 2. Okay, so looking at it, if I take 1 times 10 to the negative first and divide it by 5 times 10 to the negative 2, I get 2. And if I take that rate, 2.3 times 10 to the negative first divided by 5.75 times 10 to the negative second, I get 4. So when I double my concentration, I quadrupled my rate. So that means that ClO2, it is second order. Doing the same for the other, going from 2 to 3, there is no effect on the rate from ClO2 because it stays the same. But going from 1 times 10 to the negative 1 over 3 times 10 to the negative 2, I get 3.333. Doing the same thing with the rate, I get 5.75 times 10 to the negative 2 divided by 1.73 times 10 to the negative 2, and that gives me lost my pen, 3.33. So that is first order in hydroxide. So my rate expression, rate is equal to the rate constant times ClO2 to the second power, hydroxide to the first. Okay, so for the next slide, it says to determine the rate constant and state its units. This was a little ugly looking through the papers, and we're supposed to use experiment 2. So using experiment 2, we plug in a value for the rate, which is 5.75 times 10 to the minus 2 moles per decimeter cubed over second. That's going to be equal to K times the concentration of ClO2, which is 0.05 moles times decimeters cubed, and I'm squaring that, and then the concentration of the hydroxide, which is 0.1 moles decimeter cubed. Okay. Remember that you have to square everything in that, so I will get 5.75 times 10 to the negative 2 moles decimeter cubed second equal to K times, if I take 0.05 squared times 0.1, I'll get 2.5 times 10 to the negative fourth. In the numerator for this, I have moles squared times moles, so I have moles to the third over decimeters cubed squared is decimeters to the sixth times decimeters to the third will give me decimeters to the ninth. So K is going to be the 5.75 negative second divided by 2.5 to the negative times 10 to the negative fourth. So I get 230. Okay, now I'm going to take, I'm going to write this in blue. I'm going to take moles over decimeters cubed, and I'm going to divide them by moles cubed over decimeters to the ninth. If I divide by a fraction, I'm going to end up multiplying by its reciprocal, moles to the third. So my units here should be moles to the negative second power times decimeters to the sixth over seconds. I forgot the seconds over here. Okay, you do have to get the units correct. Okay, and you can write those seconds as seconds to the negative 1. Alright, so the next problem is calculate the rate. So, well, the rate's going to equal 230 moles negative 2 decimeters to the 6 seconds negative 1 times 1.5 times 10 to the negative second moles per decimeter cubed squared times 2.35 times 10 to the negative second moles per decimeter cubed. I'm going to end up with the answer of 0.00122 moles decimeters negative third seconds negative 1. Naming the ester, it is ethyl ethanoate. Okay, and then quantitatively the relationship between the rate constant K and the temperature T. As temperature increases, rate constant K increases. Okay, so we were given a graph. You find 2 points on the line. The slope of the graph is going to be equal to negative EA over R. So you find the slope from the graph. You should get something close to negative 6 times 10 to the third. So to get the activation energy, it is going to be negative R times 6 times 10 to the third. The units here, I believe, are Kelvin. So that's Kelvin. So it's negative 8.31 joules per mole Kelvin times basically 6,000 Kelvin. And you should end up with, and this was a negative, so it'd be a positive 49.86 is what I got. They accepted a range of numbers for the activation energy of I'm a little high actually. Oh wait, and it's kilojoules. Sorry. Per mole. Forgot the units. They accepted from 46 to 47, so I'm a little high. Okay, so deducing the overall equation for the reaction, basically you just add them up. Let's see, these two cancel, and I end up with 3 ClO negative aqueous going to ClO3 negative aqueous plus 2 chloride ions. Okay, deducing the rate expression for each step. It doesn't tell you a slow or fast, it really just wants it for each step. So for the first one, because it's part of a mechanism, you can write it for the reaction as shown, assuming that it is a elementary. Okay, and then the rate for the second one. And that is the end of that. Oh, I don't know how I did that. Wow. Oh, look at that. Oh, sorry. So that's the end of the screencast.